In this video, we will discuss one of the important method of analysis of pericyclic reaction, the perturbation molecular orbital method or PMO method, otherwise called Huckel Mobius analysis or transition state aromaticity method. It is a method for assessing whether a given pericyclic reaction is allowed simply by examining the cyclic array of atomic orbitals at the transition state of the pericyclic reaction. We are only examining the cyclic array of atomic orbitals in the transition state of the pericyclic reaction. You know Huckel's rule of aromaticity. According to Huckel's rule, a monocyclic planar conjugated system will be aromatic if it has a 4n plus 2 pi conjugated or delocalized electrons, and such a system will be stable in the ground state. Similarly, a monocyclic planar conjugated system will be anti-aromatic if it has 4n pi conjugated or delocalized electrons and consequently unstable in the ground state. Further calculation shows that the Huckel's rule will be reversed by the presence of a node in the array of atomic orbitals. For example, if a system with 4n plus 2 pi electrons and a node, that will be anti-aromatic by the presence of this node, while the system with 4n pi electrons will be aromatic if the system has a node. That means the Huckel's rule will be reversed by the presence of a node. That is why a system with 4n plus 2 pi electrons and a node will be anti-aromatic instead of aromatic, while a system with 4n pi electrons and a node will be aromatic. Okay. Thus, we can say if there is no node for a system with 4n pi electrons, it will be aromatic and stable in the ground state. Whereas if 4n pi electrons or a system with 4n pi electron and 0 node will be anti-aromatic, that is unstable in the ground state. That is according to Huckel's rule. Then it will be reversed if there is a node, that is a system with 4n pi electrons and a node will be aromatic and stable in the ground state. Here 4n pi system becomes aromatic if it has a node and would be stable in the ground state. Whereas 4n plus 2 pi electrons becomes anti-aromatic, system with 4n plus 2 pi electrons and a node will be anti-aromatic and unstable in the ground state. If the system has no node, that is 0 node, then it is called Huckel system. You know Huckel system having no node, and the array is called Huckel's array. While if the system has a node, then it is called a Mobius system and the array is called Mobius array. Application of these rules to the pericyclic reaction led to the generalization that thermal reaction takes place via aromatic transition state. For example, 4n plus 2 pi electrons having no node or 4n pi electrons having one node. That is usually aromatic according to this theory. And the photochemical reaction proceeds via anti-aromatic transition state. According to these theories, anti-aromatic transition state will be having 4n pi electrons having no node or 4n plus 2 pi electrons having one node. And so a thermal reaction to take place, an aromatic transition state is needed, whereas to proceeds a reaction via photochemical method, it has to have an anti-aromatic transition state. Or a thermal reaction proceeds via aromatic transition state, whereas a photochemical reaction takes place via an anti-aromatic transition state. That is one of the important points in the PMO method or perturbation molecular orbital method or in Huckel Mobius analysis of pericyclic reaction. Okay, thus Huckel system will be a cyclic transition state with 0 node where there is 4n plus 2 pi electron. The system will be aromatic and the reaction proceeds via thermally, or it is a thermally allowed process. If there are 4n plus 2 pi electron and 0 node in the cyclic array at the transition state, that is referred to as a Huckel system. Another Huckel system is a cyclic transition state with 0 node having 4n pi electron. That will be anti-aromatic and the process will be photochemically allowed. The pericyclic reaction will be photochemically allowed if it has a 4n pi electron and 0 node in the cyclic transition state. These two systems, the 4n pi 2 pi electron system and 4n pi electrons with 0 node in the transition state, is called Huckel system. Whereas in the Mobius system, a cyclic transition state with 1 node, for example 4n plus 2 pi electron and a node, will be anti-aromatic and the pericyclic reaction proceeds via photochemically. And if it has the cyclic transition state having only 4n pi electron but having a node, then the system will be aromatic and the process will be thermally allowed. So thermal reaction proceeds via aromatic transition state, while photochemical reaction proceeds via anti-aromatic transition state. Okay. In this method, we are considering only the cyclic array of atomic orbitals representing those orbitals which undergo changes in the transition state and assign the signs in the wave functions of this array in the best manner for overlap. Then the number of electrons and the number of nodes in the array are counted. Okay, now let us consider how the PMO method is used to analyze an electrocyclic reaction. First of all, we have to take an electrocyclic reaction of 4n pi electron system. See, for example, the ring closure of 1,3-butadiene to cyclobutene. 1,3-butadiene is a 4n pi electron system. During the electrocyclic reaction, ring closure takes place to form cyclobutene. First of all, we have to consider whether this reaction takes place via Conrotatory process, which may react either thermally or photochemically. First, we have to analyze whether this reaction is a thermal reaction. Conrotatory process is a thermal reaction or a photochemical reaction. For this, we have to draw the array of atomic orbitals of this butadiene in the best manner for the overlap and have to examine whether the Conrotatory process takes place in order which leads to a cyclic transition state having any node. We have to examine whether there is any node. If there is a node for this system, it will be aromatic because it is a 4n pi system, and it will be a Mobius system if there is a node. And if there is no node, then it will be an anti-aromatic system and is a Huckel system. We can examine. See the molecular orbital of the butadiene molecule. It is the array of atomic orbital in the butadiene, which is oriented in the best manner for overlap. And if the ring closure takes place via Conrotatory fashion, the atomic orbital or pi or p orbital of each of the terminal carbon atom has to rotate in the same direction. Thereby, the positive lobe will interact with the negative lobe of the terminal carbon atoms, and hence there will be a node because the positive lobe of this atomic orbital will interact with the negative lobe of this terminal carbon atom if the rotation is conrotation. Thereby, we will get a transition state with array of atomic orbital which containing a node. So it is the array of atomic orbitals in the transition state with 4 pi electrons and a node. Here is a node because the interaction is between positive lobe of the p orbitals of one terminal carbon atom with the negative lobe of the p orbital of other carbon atom. There will be a node, And so it is a Mobius system, and the reaction will be thermally allowed. So we can conclude the ring closure of 1,3-butadiene to cyclobutene is thermally allowed via the reaction taking place in a conrotatory process. Okay, if the reaction is taking place via a disrotatory motion, see the positive lobe of this p orbital of this terminal carbon atom moves clockwise, while the positive lobes of this p orbital of this terminal carbon atom moves or rotate in the anti-clockwise direction. Thereby, both the positive lobes of the terminal p orbitals of the terminal carbon atoms coincides, and there is no node in this interaction. So the cyclic transition state can be represented like this. See, it is the array of atomic orbitals in the transition state which represent no node or zero node, but it has 4 pi electron, and hence it is anti-aromatic. And also, you know, the system is Huckel system. Foreign pi electron or 4 pi electrons with a zero node is anti-aromatic in the Huckel's rule or Huckel system. It is a Huckel system. So it is photochemically allowed process. So the interconversion of 1,3-butadiene or ring closure of 1,3-butadiene to cyclobutene via a disrotatory motion is photochemically allowed process. Okay, now let us consider the 4n plus 2 pi electron system of electrocyclic reaction and how the PMO method is applied to analyze 4n plus 2 pi electron system. A typical example of 4n plus 2 pi system is the interconversion of 1,3,5 hexatriene to 1,3-cyclohexadiene. As in the previous case, it is a ring closure reaction. So we will take the pi molecular orbital of 1,3,5 hexatriene system that can be represented like this in order to have the best possible overlap. And if we consider the conrotatory interconversion, the p atomic orbital of the terminal carbon atoms both rotate in the same direction. Thereby, the positive and negative lobe coincide, and hence there will be a node. The cyclic transition can be represented like this. You can see it represents the cyclic array of atomic orbitals in the transition state, which shows a node, and so it is a Mobius system, and hence the conrotatory interconversion of 1,3,5 hexatriene to cyclohexadiene, 1,3-cyclohexadiene is photochemically allowed process. Okay. Similarly, if we examine the interconversion 1,3,5 hexatriene to 1,3-cyclohexadiene, whether take place via disrotatory motion, which in turn in thermal fashion or photochemical mode has to examine by using the PMO method. Then see, it is the molecular orbital of 1,3,5 hexatriene. If disrotatory motion takes place, then the p orbital of the terminal carbon atom, you can see the positive lobe of this terminal carbon atom, positive lobe of the p orbital of this terminal carbon atom rotate this direction, while the positive lobe of the p orbital of this carbon atom rotates opposite direction or anti-clockwise to each other. So positive lobes interact with the positive lobes, and so there is no node, and hence the cyclic array of orbitals in the transition state can be represented like this. And this cyclic array having no node or zero node with a 6 pi electron is aromatic, and so this cyclic transition state is a Huckel system. So the reaction is thermally allowed. Hence we can say the interconversion of 1,3,5 hexatriene to 1,3-cyclohexadiene is thermally allowed via disrotatory motion. This process is thermally allowed and it takes place via disrotatory motion. Okay, on the basis of this conclusion, the selection rule by PMO method for the electrocyclic reactions are like this. If the system having foreign pi electron with zero node, it will be anti-aromatic. The cyclic transition state will be anti-aromatic, or it is a Huckel system, and the process will take place photochemically via disrotatory motion. Then if the same system, if having one node, the cyclic transition state will be aromatic, or it is a Huckel system, and the process takes place thermally via a Conrotatory process. If the system is 4n plus 2 having 0 node, then the cyclic transition state is aromatic and the process will take place thermally via disrotatory fashion. And if the same system is having one node, then it will be anti-aromatic, or it will be a Mobius system, and the process takes place photochemically via a conrotatory motion. Here the n is an integer. Now you might have got a clear concept about what is PMO approach and how it is used for the analysis of an electrocyclic reaction. Here I conclude this video. Thank you for watching. Thank you.